And we are back, and let's get into interatomic potentials. Very, very, very important. So, why do materials bond? Well, it goes all the way back to, not all the way back, we just talked about it. We want to lower our free energy. So forget about entropy for a second, enthalpy. So, why do atoms want to bond? Well, we have this negative electron cloud. If they're too far away, they don't see each other. If they're too close, they overlap, the cores repel. But if I am right at the sweet spot, if I'm a 2r distance apart for two atoms, that is going to lower my energy. And I want to lower this energy as much as possible. So one of the ways that we can encapsulate this bonding and why bonding wants to occur is with a potential. So for example, we could look at, there's many, many, many different potentials. We will go over and you will see in your problem set many different types, but we can see one of the most famous is the Lennard-Jones potential. So this is our interatomic distance r. Here, this would be essentially our r naught, which is going to be equal to our 2r distance. So right when the atoms are here, lowest energy state. If I'm shorter, they're overlapped, they repel. High energy, bad. Here, at infinite distance, they don't see each other, poor energy. And you see that this function is a function of r and then two fitting parameters, sigma, epsilon. So there will be some fitting parameters effectively here. Additionally, remember, we can always relate the force to minus the gradient of, basically, or the force essentially between, the force between atoms is going to be minus the gradient of a potential energy. Now that's the force that's felt between the atoms. To pull them apart, like so if I wanted to pull the atoms like this, it would be basically the force like applied would be equal to basically minus the force of the atoms, as you see here. This is going to come into play later on, but don't worry about it for now. So, lots of different types of potentials, Morse, Bornmeyer, van der Waals, etc. But the Lennard-Jones potential is a very, very important one. And I could find essentially where the force is maximized. I could find, again, if I want to find the equilibrium distance, I'm just going to take that function, take the derivative, set it equal to 0, solve. You can see here a Coulomb potential. Again, fitting parameter C, function of R. You can look at, actually, the Coulomb potential right here. Excuse me, this is a Coulomb force. And you can see here, this would be our Coulomb potential here. So, last time we looked at this here. So, we said last time that covalent bonds, again, they're going to share those localized valence electrons in the orbitals. And that we can distinguish between covalent and ionic interactions when basically an ionic interaction they're going to be giving up or taking electrons. So how can we determine when something is covalently bonded or metallically bonded? Well, not metallically bonded, covalent or ionically bonded. The true answer is it's very difficult, and really every reaction or every bond is basically has some level of polar covalency. So it's never 100% covalent, 100% ionic. But for this class, we are just going to use the following convention. This is not a well-established convention in chemistry, but we'll use it for this class. If we find the electronegativity difference between our atoms to be 0 to 0.4, non-polar covalent. 0.5 to 1.7, polar covalent, greater ionic. And then again, we've talked about before in metallic bonding, all basically atoms share the valence electrons and they are delocalized. A sea of delocalized electrons. That's a great term. And that gives rise to all of those very, very cool and interesting, basically, electrical properties that metals can exhibit. And then in the next time, we're going to get into intermolecular interactions. So weak interactions, but very, very cool interactions. So we'll see you in the next video. Thanks.